Okay, so one of the problems in the chapter is 11.331, which actually depends on this theorem 11.329. So first let me read this theorem. If G is cyclic and G is isomorphic to H, then H is also cyclic. Conversely, I could have said if G is cyclic and H is isomorphic to G, then H is cyclic. G is isomorphic to H, or H is isomorphic to G. Those mean the same thing because we know that isomorphism is an equivalence relation. All right, so first question here is exercise 11.331. Prove that Q is not isomorphic to Z. Now we know that Z is cyclic. We showed that previously. Now to prove this, you will use the following proposition. Proposition Q is not cyclic. So let me give you a proof, and we'll prove by contradiction. So here's my supposition. Suppose that Q is cyclic. That means that Q is the orbit of A for some A in Q. That's what cyclic means, that there's a generator of Q. I could write this way, that Q is equal to all integer multiples of A. Now, why is that? Because my operation here is a plus, right? So when I take 0A, A plus A plus A plus A, and so on, if I take repeated pluses, what I'm going to generate are the integer multiples of A. All right? So if Q is the set generated by A, that means that Q is equal to the integer multiples of A, plus or negative, also 0. All right, but consider A over 2. Now, since the rationals are closed under division, then A over 2 is in Q. Now, this implies that A over 2 must be some integer times A, or I should say, for K and Z. Okay. And then here I should probably say this, okay, since Q is closed under division, okay. Now, so since A over 2 is in Q, this implies that A over 2 is equal to KA for some K in Z, because Q over A over 2 must be in this list somewhere. A over 2 is in Q, so A over 2 must be in this list somewhere. Now, if I rearrange this equation, A over 2 equals KA, I get A over 2 minus K equals 0, or A times 1/2 minus K equals 0. Now, by a previous theorem, I could call this actually the zero divisor property. Let me just write it that way. Call this, instead of a previous theorem, we'll call it the zero divisor property. Of the rational numbers. This implies that A is equal to 0 or 1/2 minus K equals 0. You got the product of two numbers equals 0. One or the other must be 0, and I can say or both. All right, now let's consider first whether A could be 0. Well, if A was 0, then the angle brackets of A would be angle brackets of 0. But angle brackets of 0 is just the set 0, because all multiples of A, all integer multiples of 0 are just 0. So A cannot be 0, because otherwise A would not generate all of Q. Also, K is an integer, so 1/2 minus K is not 0. That would mean that K equals 1/2. Okay. This means that A times 1/2 minus K is not equal to 0. So here we have two contradictory statements. One statement is that A times 1/2 minus K equals 0. One is A times 1/2 minus K is not 0. So this is a contradiction. This contradiction establishes that our supposition is true. Our supposition is up here at the top. Suppose Q is cyclic. Okay, so that's not true. That cannot be true. So Q is not cyclic. All right, so that's showing that Q is not cyclic, and you can use that fact to establish part A of 11.331. The other two are pretty straightforward. Just remember, you use theorem 11.329.